Good morning. In this session, I would like to demonstrate another example of using optimization toolbox in Aspen. So, a 15 cubic meters per second at 50 degrees centigrade and 1.75 bar need to be compressed to 50 bar by using two different types of compressors. You can see the choice of the type of compressor is influenced by the centrifugal compressors can handle high volumetric flow rates but develop low pressure ratios, whereas the reciprocating compressor is suited for low volumetric flow rates but can develop high pressure ratios. So to combine the advantages of each, the compression will be carried out by centrifugal compressor. You can choose an isotropic compressor while simulating. In series with a reciprocating compressor, choose positive displacement. The interpolar between the two is reducing the compressor cost is given by this equation, and the cost of the reciprocating. You are required to now minimize the total cost by choosing the value P1, the exit pressure from the first compressor. So you can try to simulate this problem. So we are using A. Choose a property model. So you are given that it should be PSRK. So try to be careful, especially when the pressure is high. You are required to use predictive equations of state. Next, simulation environment. Create your flow sheet. You have pressure changes, compressor, and then we have a heater in between them. In fact, it is going to serve the purpose of cooler. Output streams. Having drawn the flow sheet, now let us go and try to finish the problem definition. So you know the conditions. Air is entering at 50 degrees centigrade and 1.75 bar. And the flow rate of air, this is volumetric flow rate. Of cubic meters per second, 50. So we have specified the input stream. Now let us go and define the. So the first compressor as isotropic, and the discharge pressure we don't have any idea, but let me assume that it is 25. You can make any wild guess between 1.75 to 50, the outlet pressure. Let me also deal with this convergence. We don't want to make any vapor liquid check, so we would like to deal with it as vapor only. So go to the next. Now this is the second compressor, now which we need to as positive displacement. The discharge pressure of course is fixed at 50. Now we need to talk about the cooler, which is reducing the temperature, inlet temperature to 50. Assume that there is no pressure drop. Okay. That is this problem. Of course, we have not addressed the costs. We will try to incorporate. So you can see 1.75 to 25 and 25 to 50. The required compression is handled by the two compressors. Whereas here you can see when the pressure is increased from 1.75 to 25 in the first compressor, the temperature is increased to 540, but the cooler is bringing it back to 50. Then the temperature is increased to about 151. Now, after this, now let us try to incorporate the optimization toolbox. Next. So, what is the variable that we are interested in? In fact, we know the inlet flow rate, volumetric flow rate, which has been given as 15. So, let us define that as a variable, Q. So, this is a stream variable. In fact, it is a stream variable. This is standard volumetric flow. Input stream S1, component is of course only one component, but the units that we want are cubic meters per second. Now this is one variable which is involved in the objective function, and the other variable is the intermediate pressure or the exit pressure as the block variable. Block is B1, variable is the pressure, specified outlet pressure. Now what is your objective function? You need to minimize the cost. The first exchanger cost is given as 70 times the value of Q plus 1600 multiplied by P1. I think is it P1 by P0 or P1 by P0. We know P1, which has been defined here. P1 divided by P0 is 1.75, the inlet pressure, plus 200 multiplied by Q plus 800 multiplied by P2 by P1, I think. P2 by P1. P2 is 50 by P1 is anyway a variable. So we have defined this. Are there any constraints that we need to deal with? This is also an unconstrained problem. Now we would like to vary the intermediate pressure or the pressure from the exit of the first compressor. So the inlet pressure is 1.75 and the outlet pressure is 50. So let us take somewhere in between. We expect the answer to lie, the optimal solution to lie. So having defined this, you can run the problem. You can see we were able to come to a convergent solution. The method used is, look at the results, stream summary. Now you can see 1.75, 6.61 is the exit pressure from the first compressor, and finally 50. We already saw the reciprocating compressor, the pressure ratio will be higher compared to the centrifugal compressor. So probably that is obtained here. And this is your objective function, cost value, as per your definition. We started with 25 as the inlet guess for the exit of the pressure exit from the first compressor, but this is going to be the optimal pressure at the exit of the first compressor. This is how you will be in a position to use optimization toolbox. We have seen in the previous problem, especially two CHTRs of equal volume, a constrained optimization problem, whereas here, this is an unconstrained optimization problem. So let me close this session.